So while we wait for everyone to join, today is the set covering one, the knapsack. Then we'll go through the fixed charge, some parts of that exercise, and I'll tell you which location exercise you need to focus on. Well, there's two, but yeah. And then tomorrow we'll continue with the exercises review of classes 1. And on Thursday we'll do the last topic of the week, which is fairly easy. We'll start with it tomorrow, but it's fairly easy enough to do on a Thursday. Then go through the exercises and then you'll be ready for the next test. Right, so let's see how it goes. Just want to make sure everything's plugged in. There we go. Right, so it's going to be a fairly easy topic. It's just sometimes it requires a bit of, well, you saw now with most of the IPs, requires a lot of logical thinking to set up. So you should know how to deal with binary and how to deal with integers, and then play around with logical constraints to set that up. But it's very important that you define your decision variables so that you know exactly which ones are binary, which ones are integers. And then if you have any conditional constraints or logical constraints, then it's easier to set up because you know exactly what you can use to set that up. Then just a reminder, if let's say you had the IP like yesterday, where you had some xij values, which were integers, and you had y values. Well, it could have just been xi, doesn't matter, but x variables that are integers, and some y variables that are binary. When you relax your IP, you remember you first need to relax the IP and then solve without thinking about integers or binary so that you can get an optimal solution first. So you would have basically said when you relax, it's just xi greater than or equal to 0, same as y, it's just greater than or equal to 0, so that you can solve to get a solution. Then I gave you that tip, which I'll now give properly. For the ones that are binary, you would then go to each of them. So let's say you had 4 y, so y, 1, 2, 3, and 4. You would literally have to go in the relaxed IP and specify less than or equal to 1 for literally each of them. This just helps you to have an optimal solution where your variables that should be binary are not going to give you answers way larger than they actually should be, which makes it harder then to get back down to between 0 and 1. So you always start with adding constraints for your binary variables additional before you get an optimal solution. Then you solve with either dual or primal. You should know by now that you can use two-phase as well instead of dual if you want to. But either or dual is when you've got different signs, like you've got a less than, a greater than, and equals, but not just less than signs. Whereas primal, you only have less than signs only. That's how you know what to solve with. Then you get an optimal solution. If your optimal solution has integers where there should be integers, well, then you don't have to worry about those values. If they have binary values where there should be binary, then don't have to worry about those. You only worry about those that are not what you want them to be or what they should be. So let's say you had x1 being an integer, x2 being a fraction, x3 a fraction, and so forth. Then you have your y1 as a 0.5. Maybe your y2 is already binary, and your y3 is then maybe a 0.8. So when you start solving now, you'll then go with the one that's close to 0.5. So branch and bound simplex or cutting plane or cutting plane. So then you'll go and say, okay, which one is closest to 0.5? So right now, if I take all the fractional values, so I'm not even looking at the integers because they're sharp. So fractional value 0.2. This one, the fractional value is literally what it is. This is already binary. So I want it to be binary, not a value of 2 or 4 or 6. That's why these constraints are very important. And for this one, 0.8. So we've got two of them that's closest to 0.5. So I start with the smaller subscript. However, right now we've got x's as well as y's. So you can actually take the smaller subscript, which is 1 for the y, but technically it doesn't matter, just to make it clear, especially if you're not going to be filling in on the assessment queue, then it technically doesn't matter which one you start with. You could have started with the x's first and then work your way through there with each time checking which one's closest to 0.5. You'll eventually get to doing this one as well. So you'll just have to then keep track of if you're working with the x's. So let's say I start with x2. If I branch on that, I'm going to have a problem where x2 is going to be less than or equals to 2 because the value is 2.5. And you're going to have an x2 that's greater than or equals to 3. So you're trying to move away from the 2.5. However, let me ask you guys, what do you think am I going to do with y1 if I wanted to branch on y1 first? Perfect. So for any binary values, you're always then going to go with a less than or equal to 0 and a greater than or equal to 1. Because if they're binary, you either want to go to this one or this one. So if you make greater than or equal to 1, you're hoping to find a y that's 1. If it goes past that, then you're not going to use it because obviously it should not go past that. You can't use equal. Okay, you can use equals, but it's much more work. Guys, you know by now, if you have an equal sign and you put it in a constraint, you're going to have a less than as well as a greater than sign. You can do it. It's just not so fun. And using the less than or equals to and greater than or equals to will still give you the same purpose. So I hope that helps you, but I'm not going to go more into details. That's just to give you a basic idea. All right. And no, you pick the one closest and then you can go either or. But I just showed you what to do if you decided to go with x2 first. And then I showed you what to do if you decided to go with y1 first instead. Right, but you won't do them in the same sub-problems. Right, you do them one at a time. Not exactly the same, but you'll eventually get to a branch that will sort out your y as well. Remember, you don't stop branching after just one. So this might give you a solution where y1 becomes a 1 and then you smile, but maybe it becomes a 0.8 instead, and then you now go with this one and then you branch further. So it's still going to eventually get to your other variables as well. Just going to take much longer because you have much more variables to take care of. Right. But your final answers will be the same. Yes. Right. Cool. Okay, so I just wanted to give you that as a recap, but that was not actually the topic. So let's go on with the topic. Okay, so for set covering now, we can start with this one. So for set covering, it's very similar to your project management topics where you had certain, how can I say, networks that had to be covered or certain locations. I'm not sure what scenarios you guys use, but it's very similar where you could have said one can cover, let's say, this one and this one, but this one can cover this one, whereas one don't reach that one. So it's very similar to that. So that's thinking that you should have when you do any kind of set covering problem. So just to show you, let's get into it. So there are 6 cities, cities 1 to 6, whether they have names or not, it's cities 1 to 6. Then the metro must determine where to build fire stations. Okay. The Metro wants to build the minimum number of fire stations. So already kind of hint towards my objective is to find the minimum number of fire stations. So somehow I need to either count them up or sum them together. Then we also need to ensure that there is at least one fire station within 15 minutes of each city. So that's a constraint. We now have some kind of constraint there. Then they give us time within minutes that it takes to drive between the different cities in this table. Right. So the first thing that I want you to take note of that will also apply to the traveling salesperson is that this is a symmetrical table. What do you think that means? You can give me some kind of information on what do I mean with this table is symmetric. 6 by 6 is one way to identify, but there's more to it. But 6 by 6 is already a indication that it could be symmetric. Yes, it first must be square before it can be symmetric. So it must be square before it can be symmetric. So good observation. What else? Oh, I like it when so many people are typing. You guys are fresh and awake. 36 equals 31 and 31 equals 36. So the from and the to and the to and the from, yes, the values are given twice. Well done. Let's see what else, how else you guys explain. Let's see if someone else has something interesting. But that's the concept. Yes, yes, yes. Yes, 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 yes. Very good. Okay, so if you don't get what they're saying in the chats, we're basically saying if we go from city 1 to 2, that is 10 minutes. But city 2 to 1 is going to be exactly the same. It's going to also be 10 minutes. So we don't fill it in because it's going to be the same. If you draw a diagonal line, the values are going to be duplicated on the other side. So let's fill them in. What would be the value at city 3 to city 1? So x3, 1. Good. So you're looking at city 1 to 3, which is 1 to 3, which is a value of 20. So it's going to be symmetric, meaning this value will be exactly the same. Very good. What about city 3, 2? X3, 2. Give me x3, 2. Sorry, x3, 2. What would 3, 2 be? Good. So we got check 2, 3. That's a 25. So 3, 2 must be also 25. So you're basically filling it in like this. What would city 4, 1 be? 4, 1. Perfect. 1, 4 is 30. So 4, 1 is also 30. 4, 2. 35. You guys are quick. 4, 3. 15. 5, 1. Kenneth is the fastest there. Anyone else? 5, 1 is, yes, 30. What about 5, 2? 20. 5, 3. 30. What about 5, 4? 15. 6, 1. 20. 6, 2. 10. 6, 3. 20. 6, 4. 25. And 6, 5. 14. So if you draw a diagonal line there, you'll see it's a symmetrical table. You can flip it on each other and see the same values, like flip a page on each other. This concept is very important also for the Queen's problem that we will do and traveling salesperson, which is also going to have either a symmetrical or an asymmetrical table. All right, so we can fill in our values. If you want, you can take a picture. But while we are busy, why is city 121 just a dash? Yeah, you're already in that city, right? So if you're going from city 121, you're already in that city, so you don't need to worry about a certain amount of time to travel to that city. Of course, you could have a problem where it requires time within a city to travel to different regions, then it will just be a bigger table, right? But the same concept will still apply. Like, how many minutes does it take? So that if you then set up your constraints, you consider the amount of time and set it up for that. Right, but let's see, how can we do this? So right now, we first start with the fact that we want to be able to know how many fire stations there will be. And we want to also think of how can we set up constraints to do this minutes type of thing. Right, so we can either think of xi or xij. So if we use xi, we can say city 1, city 2, city 3, but it might not show us where we're going from and where we're going to. However, it does help us exactly if we work with this, which I'm going to show you exactly how we can do. So if you use Xij, it's going to be much bigger IP, which is very unnecessary. So you'll see when we do it like this, if you had to go Xij, it would be quite inefficient. It could work, but it's not that great to use. So usually if you have, let's say, a problem where you have to cover certain regions or areas, or disks or whatever, you're covering it, meaning this one can take care of those two and this one can take care of those three, then you're going to just work with an XI unless it's really necessary to go the XIJ route. So what I'm saying is city 1 goes to city 1. So it's the same thing. So saying the top columns and the rows are exactly the same. So it's not just regions to cities, it's literally city to city. So in that case, you can already make like a pattern like, oh, okay, if I see it's the same thing, most likely it's just going to be an XI, right? If it doesn't work to set up your constraints in that way, then you'll then go the XIJ route. But if it was, let's say, region to city, then you'll think IJ, because then I need to know which region to which city, because now they're not the same. All right, so just to give you some advice what to look out for. So we go with XI, and let's see how can we do it this way. Right, so XI, so I being the city, and we've got cities 1 to 6. So we're going to create a small table to check what is covered by which cities. So without creating a table, let's quickly look. If I say city 1, which cities will be within 15 minutes distance, 15 minutes time? Which ones? Good. So you only need to read it one way because it's symmetrical. So you don't need to read it from this way and from the left. It's only one way if it's symmetrical. If it was not symmetrical, then you'll have to look at it from both ways, in terms of your setting constraints from the one and from the other one. So meaning from city 1 to 3 would be different than from 3 to 1 if it was asymmetrical. But it's symmetrical, so you only have to go, okay, if you're going to read it like this, great. If you're then going to say, no, I prefer to read it row by row, that's just perfect. So we're going to read it row by row. Let's go city 1. City 1, if I go from city 1 to 2, it's definitely going to cover city 2 as well. So if I put a fire station here, it's going to cover city 2 as well. City 3 and 4 and 5 and 6, they're all 20, 30, 30, 20 minutes away. So it's too far away. We said it must be within 15 minutes. So it's going to cover only those. If I put a fire station in city 2, which ones would that cover? Good. Just to make it clear, we're actually setting up this table. So this one, city 2, would cover then city 1. So I'll put a circle there to say, oh, it's covered by city 2's fire station, but it's actually just put in city 2. I'm just showing what's being covered. City 2 will also cover then city 6. So I go and say, okay, city 6 will be covered by that circle fire station. So if you wanted to create a table so far, you would then go and say, if I put a fire station in 1, it's actually going to cover itself, because if it's in itself, it's definitely within 15 minutes, and it's going to cover city 2. If I put a fire station in city 2, it's going to cover, well, itself, yes, but it's also going to cover city 1 and city 6. So we're setting this table up that you saw before. What about city 3? What will it cover if I put it in city 3? We would put a square. Good. So 3, you'll see no, 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 no. Now 15 minutes is still on the dot, so we'll take it as. But you could have technically argued and said, no, within. But yeah, that would be your argument then. Right, but we'll take this one. And itself, of course. So itself is covered, and then it also covers 4. So that one. So we can say if it's 3, it's going to cover itself and 4. What about city 4? City 4 will cover 3, itself, and 5. Very good. So 3, itself, and 5. So you'll see there, I'll say 3, itself, and also 5. What about city 5? Getting quicker. City 5 is going to cover 4, itself, and 6. 4, itself, and 6. So I'll make a what sign? A question mark. Question mark. 4, itself, and 6. So I'll make arrows to show you this goes to that. That one can also cover that one, just to show you example if you wanted to do it like that. What about city 6? You guys had those answers ready, hey? 6 can cover 2, yes. It can cover 5 and itself. 2, 5 and itself. Well done. So if we take 6, we can then go and say, oh, okay, it covers 2, 5, and obviously itself. Okay, so obviously you can then already kind of determine what would be a good solution, but obviously the bigger nodes or the more nodes you have, the more difficult it is. So we set up an IP that you can then solve with all our algorithms. Right, but now you see where this table comes from, and let's see how we can use this table. So that's where this table comes from. Right. So first off, you'll see our decision variable is saying whether a fire station is going to be placed in the city or not, where I refers to which city it is. So in our objective function, we're just minimizing the amount of fire stations. So if they're being placed, the x value will be 1. If they're not placed in that city, then it's going to be 0. So if this was the answer, it's not, but if this was the answer, how many fire stations would have been placed? Perfect. You go add them up, you'll see then it would have been 4 fire stations. Because they're binary, you're literally saying 1 plus 1 plus 1 plus 1. So if you used xij, it could have worked because it will cover from and to, but the problem is, let's say city 1 covers like we had here, 1 and 2. You'll then have x1, 1 and x1, 2 both as 1s. So if you add this up, you'll be saying there are 2 fire stations, which is not true. You only have 1 fire station in City 1. You could have another fire station in City 2, but I'm just saying if we look at this specifically saying 1 covers 1 and 1 covers 2 as well. So the fire station is in City 1, which covers itself and 2. So you only have 1 fire station. However, you'll be counting it twice because of it saying it goes and covers 1 as well as 2. So then you'll say 2 fire stations, but it's not true. There's actually just 1 fire station. So the xij would not have been a good idea for this specific example. All right, so let's see the constraints. Much easier than we think. So the constraints are literally saying we want to make sure that all the cities are covered. So you're definitely not going to use less than or equals to 1 because then it's going to allow them to be 0 because you're trying to minimize. So it's going to allow zeros, which is problematic because if I look at this specific block here, I'm saying I need a fire station there in order for me to cover both of those. I can have one here as well, sure, but to make sure that those 2 are covered, I need at least 1 there, right? So you don't want to allow zeros in this case. So would you use equals to 1? Also not, no. Not, also not, sorry. Equals 1 will limit it too much because remember, nothing stops you from, let's say, let me use a different color, from saying, I need 1 here, and I also need, let's say, let me just see. Well, we can let's do this one here. So nothing stopped me to say I need 1 here as well. But 2 is in both constraints. So I should not limit it to say, no, it can only be in 1 constraint. So then it can't be that constraint, which means you're limiting too much. So you're then going to allow it to be more than 1 to say that it can be in more than one of those variables. So I can have 1 here and 1 here because I maybe need the fire station specifically in x2 so that it then can duplicate those values technically. It's not a problem, but then you have to consider the greater than or equals to 1. Right, so that's why it's greater than or equals to 1. The 1 being I need at least 1 fire station, right? If I have more, it's okay. It's just covering different cities if I need more, but I need at the very least 1. Now we go and set it up. So I hope you can already pick it up. So you can see that constraint 1 is literally that first block. So if I set up a constraint for that block, I'm saying that for 1 and 2, city 1 and 2, I need at least 1 fire station there to cover them. Whether it's in 2 or in 1, we don't know yet. But it's going to just be purely x1 plus x2 greater than x1. The next one, I need at least 1 fire station in either city 1, 2, or 6. So you'll see the constraint is 1, 2, or 6. The third one, I need it either in 3 and 4. Fourth one, I need it either in 3, 4, or 5. In the fifth one, 4, 5, and 6. In the sixth one, 2, 5, and 6. So you'll see the others there as well. Right, and then of course you specify your sign restriction saying that they are binary in fact. Do not say they are greater than or equal to 0. I mean, it's quite obvious. They can only be 0 or 1. Don't add stuff you don't need. If you solve this one, this would have been the solution. So let me ask you, what is the solution? Which cities are there fire stations? Which cities will have fire stations? If you look at that solution. Yes, cities 2 and 4. The rest don't have fire stations. So you've got a total of 2 fire stations. If you had costs involved, the cost would have been in your objective. And then this value will not be the number of. Then you just have to be careful to say, okay, I'm literally just going to count up my amount of X binary ones, and then I'll know how many. So just be careful. So if this was maybe costs involved with how much it costs to build a fire station, then you can't go and say that value of maybe, I don't know, 200 is the amount of fire stations. Then you literally go to your answers and you go count up how many ones do you have. Then you can tell me how many, just to make it clear. All right. So let's see if it works logically. If a fire station is in City 2, City 2 will cover 1 as well as 6. Yes, yeah, but no, that's not going to be a good answer. If we look at 4, 4 is going to cover 3 itself and 5. Are there any cities left that should be covered, or are they all covered? Even though there's no link between all of them, it doesn't matter. Yes, Caitlin, all of them are covered. All of them are covered by fire station. Where are they built? In City 2 and City 4. Right. Yes, Armandre, perfect. If they are not binary, you have to go in your solver, add a constraint, highlight your answers, and say binary to get those. Perfect. Right, so you highlight the variables that should be binary, specify binary. If there were other variables like our example from yesterday, like this, then you would go on solver, and for the y's, you will highlight the answers where you have all your y's. You'll say bin for the constraint. And for the x, you'll highlight all your answers for the x's, x1, x2, blah, 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 blah. And you'll say int for those. So yes, you can do that to check your most best answer. Right. But that's it. You guys okay? Did you survive? Min Z is just to have the minimum amount of fire stations. So that's why I said you literally count them up at the end to get the minimum amount. If you wanted, let's say, minimum cost, so let's say each of them had costs involved, then you will have coefficients here like a 20 and a 30 and whatever here. So then your objective will not be about the number of fire stations, then it will be minimizing costs of building fire stations. But inside, you'll still work with the number of. So at the end, when you solve, you'll then just count up the ones to see how many fire stations. Right. No, not sometimes if we feel there's a need for it. But in most cases, you should be able to identify that I'm actually doing a set covering type of problem. Because obviously in real life, no one's going to tell you, oh, this is a set covering problem. And then you're like, oh, yeah, okay, now I know what to do. Right? So obviously, look for some patterns, but they work very similar to previous ones. As soon as you see this one should cover that one, and this one should cover that one in any kind of scenario, then you're like, oh, okay, this could work. But all these IPs could have elements of the other IPs. I mean, this set covering formulation could have had some kind of fixed costs involved. Then you could have had a Y, right? But just to make it clear. I'm wondering mostly week 2 or week 2 and a bit of week 1. I do not know. Um, I just know usually the focus is week 2, but I cannot say there's none of week 1. I can't say that. All right, so study everything. And it helps you for the summative, which I'm going to give you a heads up. The last week is quite a bit tough for a lot of students, usually due to calculus. It's not difficult. I'm just saying it's a bit tough due to calculus. So then you already have the other topics kind of covered and you can focus on week 4. Right. So just some advice. Right. Alright, stop making me laugh. Okay, but that's pretty much symmetric. Not quite, Anika. This could have also been an asymmetrical table. So if it was asymmetrical, just to show you how to work with it, you'll work with it the same way. You can still do the set covering, but let's say this was a 20, this was a 40 and a 15. Then it's asymmetrical. So it's not the same going from and to. So if you now go and say, what does city 1 cover? You have to first look at it row by column. So you'll do, okay, this one, itself. Okay, so it's 1. 1 covers 1 and 2. But then you also have to look at what if it goes from um, city whatever to city 1, because then it should also cover that. So if there was maybe here a 7, you'll then go and say, okay, it covers itself, which I do have already, but it also covers then 7, which is from, let me just make it clear, it's x4 1, but it's still city 1 that covers that one. So you'll go then both sides, if it makes sense, to just make sure you have it covered. So you'll then go and say 4 would also then help us cover 1. Will it though? No. This was not a good example, to be honest, because you'll have to then have some kind of reason as to why. So, like, why is going from 1 to 2 different than 4 to 1? So maybe you have to take a detour from 4 to 1. So in that case, you would literally only look at it when you look at 4, 2, 1. So I hope that makes sense. It depends clearly on completely on the scenario. Like, what do they specify? Like, why is it asymmetrical? And then you think, okay, if I go from 1 to 4, it takes 30 minutes. So if I put it in 1, will it cover 4? No. But if I go from 4 to 1, yeah, that will cover. So in this specific scenario, whether it's asymmetrical or symmetrical, it will work out exactly the same. For traveling salesperson, that's now quite a different story, but that's a topic for next week. All right, so for now, whether it's symmetrical or asymmetrical, it will work out the same. Right, if let's say you want a pattern to know whether it's set covering, you're looking at something in terms of literally the keyword covering, like this one will handle this one as well as this one. This one will take care of this one and this one. Or I can put a file in this folder and this folder. So it's kind of like it covers more than one thing, then you use this approach. Okay. Right. But if it's like the traveling salesperson, I'll teach you how to deal with that. Right. Because then the variables will be different. Because then, so Marizon, if you have asymmetrical, not in this example where it's going to work out the same either or, but if you have asymmetrical, you'll usually go with the xij route because you want to know from and to is different from to and from. So if they're different, we have to then consider both ways. So then you'll have to use xij, you're forced to, because you're looking at from and as well as to. So from 5 to 1 and 1 to 5 is not going to be the same. So then you need xij. Right. But for this specific problem, it's not necessary. So just to make it clear again, for this specific problem, if I had a 7 here, if I put a fire station in city 1, it's going to cover city 4. not city 4. No, 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 because of the value being 30. However, if I put it in fire station 4, it will cover city 1. So if I say then my table 1 will cover 1 and 2, it will not cover 4. But when I create a constraint for 4, I'll include 1 there. It's not a very good example for this example, unless if I specify something like, oh, there's some kind of detour going backwards, or you have to drive a very longer road. um, you know, those flying saucers. So one side it's shorter if you take the other route to that side, but if you go the other way around, it's now a kind of a circular motion, so it's a longer distance or something in that line. Right. But that would be traveling salesperson more. You can check the exercises if there's something, but I'm not sure if there's something, but it will be still the same process. You just check what is covered and then you create constraints based off of that. So it will work exactly the same as this. You just have to think what will be covered if you place it there and then set up a constraint for that, right, for each of those. Let me just close this slide. So obviously the exercises are important. Please do the exercises. For example, I just quickly opened this morning the location exercise. Those PDFs are quite useful. I don't give answers for everything, so if you have a question, you're more than welcome to ask, or form some study groups and um, talk about your logic there. But these exercises, please, they are quite useful. A lot of things appear again, but with with a different scenario. So it helps you apply the concept to different scenarios. So please do the exercises, please, to get into. You're not going to get the exact same scenario, but it works very similar. Right. I wonder what the set covering looks like. Let's go have a look. But that location first exercise and the disk one as well, very nice exercises for tests. Just hint into the set covering. Let's have a look. Yeah, this one was a very, very nice one. You're still covering stuff. So you're still saying if I put a sales rep in A, it will be able to take care of B as well as C. I'm not saying it does, I'm just saying that's what you're going to be reading into. Just a very difficult one. So I'm going to warn you that it is a difficult one, but it's a good difficult one. That one I did give the scenario, the answers, if I'm not mistaken. For the other one, I hope you also pick up this. You could have done by Venn diagrams with peer project management type of topics, but the idea here is to set up an IP. And when you have an IP, you can solve with an algorithm. So the idea is literally the IP. Don't try and sit there and like, okay, let me quickly solve this. That's not the purpose of this. You want to set up a model that you can use to solve. All right. So the bigger the problem, the easier it is to use in, let's say, an algorithm that was already coded that you can just run, basically. All right. So that's the idea. I hope you guys are surviving a bit. Still okay. Danila, I saw a private chat, but it's blank, so I don't know if that was like an accident or something. If not, just send a message again. Not sure what happened there. I just have a blank there, and I'm like, I don't know. That's like, did my Hyperflex break? I doubt it, but yeah. Okay. um, knapsack. The knapsack problem. So I want us to do this while we're fresh and ready, right? So we're going to do this one, get to the algorithm, and then after break, we'll look into going through the fixed charge exercise a little bit. Then I'll tell you which location to make sure you do before we do anything on that, and which knapsack to make sure you do. And then let me think. Probably I will tell you which Bed covering would be a good idea. But let's see. Okay, let's start with knapsack. Well, we're still awake and ready to take this on. All right. I just want to quickly go open the practice questions that we have for this week while I'm at it. Let's see. Almost there. All right. Looking for the correct one. There we go. Week 2 practice questions should also show. Just remind me by Thursday to open the answers well if I don't remember. But yeah, the questions are there. The mostly it focuses on the stuff that the knapsack and queen and fixed charge. But obviously, like I said, now those exercises in the PDFs are very useful for the other topics like set covering and location. But fixed charge, you can focus on that one as well. Right, knapsack. What is a knapsack? You can see it's a bag, but what is a knapsack? Who knows? What is a knapsack? Some of you probably sitting there and Google like, what's a knapsack? What is a knapsack? Not a knapsack like in sleeping, hey, but like a nap, like KNAP. Knapsack. What is it? Rishka, a yellow bag. It's not necessarily yellow, but it's a bag. It's a backpack. Yes, that sounds better. So it's a backpack. We refer to it as a knapsack due to the fact that it's actually a well-known problem. So the knapsack problem is actually a well-known topic in linear programming. So the knapsack. All right. So the knapsack is kind of like a backpack, and when you go backpacking, you have to make sure that you pack all the necessary stuff and still not going above a certain weight because you still need to be able to travel and keep on carrying that weight. So that's basically what it's about. So the knapsack problem, there are different variations, but we will be focusing specifically on binary. So the binary knapsack problem. There are different kinds. Guys, you can work with integer knapsack problems. You can work with a combination of integer and binary. Um, there's some where it is not multidimensional, meaning you don't have a lot of x variables, whereas with us, we're going to use a lot of x variables. I mean, if you think you have x1 and x2, you can draw that on an x1 and x2 axis, but we'll then have now like x1, 2, 3, 4, 5. So you'll have quite a lot of dimensions that you're working with. Luckily, you're not drawing anything, but just to make you understand. Right, but let's get to it. So if we're going to set up a small IP, because the knapsack problem is a very small IP, you only have one constraint. So usually what you do with the knapsack problem is you'll have something that you want to either maximize or minimize. So that would be objective function. And then you'll have some constraint that you want to limit, which in most cases would be the weight that you want to limit. All right. And the max would normally be the worth that you're getting out of what you're putting in. Right. So maybe the most amount of food or the minimum costs in this case. But you want to then focus on what should be your objective for this bag, and your constraint would be what do you want to limit. Right, so that's going to be your knapsack IP. And when you have the IP, you can solve with branch bound simplex, counting plane, There are other kinds of things that you can solve, but that's your focus. Right, but after that, I'm going to show you the algorithm, which is called literally the knapsack algorithm. It's also a kind of branch and bound method, but it's not simplex. Guys, simplex is like primal and dual, which you have to actually do pivots and tables. Whereas the knapsack algorithm is not that. You're not making tables where you're going to pivot. Yeah, you're going to branch, but not no pivoting like we normally do. Okay, so let's see which boxes should be chosen to maximize the amount of money while keeping the overall weight under or equals to 15 kilograms. So first of all, make sure if you're saying 15 kilograms that you use the measurement kilograms for everything else. Um, but if I give you a constraint, you can automatically think that whatever other values you're given, that will be then what you want your objective to be. Because if there's no limitation, then that should probably be your objective. Okay, but let's get to it. We want to maximize the amount of money. So each item that we can put into this knapsack has worth or some kind of monetary value. So we're going to be looking at those values as our objective function values that you want to maximize. I mean, money you want to maximize unless if it's costs. Okay, so we're maximizing if it's in terms of what value it has to you. If you want to minimize, it's anything to do with costs or things that you do not want to go over a certain amount. Okay, then we want to make sure the weights are limited to less than or equals to 15 because you do not want to go over that weight. So that's going to be your constraint. Now, in this picture, it's very hard to know which one will be x1, which one will be x2, which one will be x3. We will kind of hint towards what should be what on assessment Q. You probably saw the assignment I say 1 is this, 2 is this, 3 is this, and then you have to identify what about 1, what about 2. Right. If I give you wrong options, just don't pick the wrong one. But the order of it will be given somewhere to help you identify which one should be which one in terms of numbering. Okay, so let's see. I can literally just say, ta-da! So items 1 to 5, I told you I'll guide you to which item is number 1 and which one's number 2 and so forth. But you saw there my objective are the values or the worth of each box that you want to put on this in this knapsack, but you're not going to put all of them because there is a weight limitation, and you can clearly see the one box is already like 12 kilograms. So if I put all of them, I cannot because my limitation is 15. So I cannot put all of these items in. So the whole objective is to then say my decision variables are going to be either we put the item or we don't. All right. So you either put it or you don't. The constraint is the values in terms of kilograms. Remember, you can't go and say 15 kilograms and then not have the kilograms because then you're basically saying, I have this item, plus this item, plus this item, plus this item. I can't have them all, but maybe this one's 0. These items I plus together and 4 less than or equal to 15. That will not make sense. That's just the number of items if you put it in terms of binary, which it is. And this is the kilograms. You can't compare the two, right? So you need those coefficients just to make it clear. Okay, then you specify as binary. That's the knapsack IP. Now we can get to the algorithm. Right, so this IP is purely for you to use something like branch and bound simplex or cutting plane. But we're going to use an algorithm which is not simplex, not simplex. Right, Mishkar, no, you don't have to put the kg. We normally just focus on what is the value, because if they're all kg, then you don't have to specify. But if, let's say, these values were grams and this one were kilograms, you'll have to convert one to the other. So then specifying would be very useful because then I can see exactly, did you go from this to this or did you go from this to this? But if they're all in kilograms, no need to specify that it is kg. You just say 15, for example. Right. If you solve a binary, that's your solution. But I told you I'm going to teach you an algorithm, and we need to get to that solution. Right. It is a type of combination problem if it's binary. Right. So the knapsack algorithm working with binary values is also a combination type of problem. So you're going to work with different combinations while branching. Right, let's see. Okay, let me get my journal. So I'm just going to rewrite quickly. So we have a max. Maybe you like purple, but I want to work with black. Max z equals 4x1 plus 2x2 plus 2x3 plus x4 plus 10x5. Then subject to 12, x1, 2, x2, x3, x4, 4, x5. What's the coefficient of x4? Just to make it clear, what's the coefficient of x4? Thank you, it's 1, right? So the first step in the knapsack branch, I'll always say B and B. Not that it's a bread and bed, what a bed and breakfast, but branch and bound. Okay, it's not a simplex. Simplex algorithm is where you have to do pivots of tables. It's not that. This is specifically the knapsack branch and bound. All right, with the knapsack branch and bound, your first step is to kind of get like a ranking table. So a ranking table to determine what would be the best route to take. So the most efficient route to get your most optimal answer. So you don't literally have to do all the combinations. In most cases, you'll see, oh, I'm going to actually do all of the branches, but from the ratio test, you're technically not doing them all. Right, but in some cases, they might go through all of them eventually anyway. Right, so let's see, but it helps you to not do stuff again and again and again. So this ranking table is something you're going to reuse over and over until you're done. Now, for the ranking table, you use Z whatever. So if it's X1, it's Z1 over C1. So constraint in Z. So Zi over Ci. Let me just do that. Okay, so let's see how we can deal with this. So just to give you some information with regards to this, even though you can just from now on remember it will always be Z over constraint, but just to give you some information. So if I had, let's say, a value of 1 x1 over 1 x1. So if I get that ratio or proportion, it's just going to be a value of 1. Whereas if I have something like 500 x2 over, I don't know, 10 x2, that would be a value of 50. Now we always start with the largest value. So in this case, you'll see the values are much smaller to work with, but you always work from largest to smallest by actually ranking your table. So you're going to work from largest to smallest. So the 50 would be the value that you are going to work with. But I want you to see, why do we go with the bigger value? So we go with the bigger value because it's going to give us more in terms of the worth and less in terms of the constraint. in proportion to that variable, of course. But the focus is going to give you more in terms of your worth. Now, if I say 10x3 over 500 x3, what would that value be? 0. How many zeros? Actually, just want to make sure you guys are still with me. How many zeros? Thank you, 0.005. So that's the smallest value. So I'm going to stay away from this one because as soon as the top is larger in terms of my Z value, smaller in terms of my Z value, it tells me my worth is less and my constraint value is more. But with this kind of my worth, and I want my constraint to be less. So I want that value. Now, even if it's a min problem, you'll still work with the same concept in your ratio because it's still the proportion that you're dealing with. It's still working with the proportion of Z in terms of the problem. But it's still the proportion, this on top of this on top of this, to see what is the Z value's worth on top of the constraint value's worth. Right. So that's the idea. Well, we're not choosing yet. We're just saying that's going to be our first order, so our first ranking value. So normally, if we were to literally swap this around, which would not really make sense because why would you worry more about money than your poor back carrying that amount of kilograms? But let's say you would swap it around and say, I want to minimize the amount of kilograms. So the 4 and the 12 and the 2 and the 1 and the 1, and I want to maybe make sure that the money's worth is more than or equals to, I don't know, maybe I want more than or equals to 200 rand, I don't know. Oh, dollars, it was dollars. Maybe I want that amount. So in that case, you're still going to work with the same principle of, okay, this would be a 12 over 2, which is 6. This would be a 2 over 2, which is 1. So you're still going to work going from largest to smallest to rank it in terms of this one's proportion is still taking the one value further away from the other. So your Z is still further away from the other one. But when you now start solving, you will see when we solve, we actually constantly look at, are we meeting our constraint? And if we do meet our constraint and there's no more branching, we go and calculate the Z. When you choose the final answer then, your minimum would be in our case, our maximum Z answer will be the best. So, but when you calculate, you'll check then for a max problem, you'll keep on checking that your constraints are less than, but for a min problem, you'll keep on checking that your constraints should be more than. Is it really bad or is it okay? Because you can't do much about it. Walter is saying shop. It's still that bad. So I just said, if it's a min problem, you'll still work with the same process, but when you check your Z values, you're going to use the minimum value. If it's a max problem and you check your Z values, you're going to use the largest value. Because with the knapsack problem, you have to literally keep on checking, keep on checking. So you keep on checking to meet your constraint. If you do, you check your Z. If it doesn't meet it, that's an infeasible branch. Right, let me just make sure you guys are still hearing me and still going on. It's still okay. better. Awesome. Okay. So you'll still work out the same way, just obviously when you compare, it's going to be different. I just say that this example will not work because it's very unlikely that you would rather minimize the kilograms and then have a certain amount of money you want to put in. But I guess if you're going to be, I don't know, selling your stuff eventually and not eating it, then money is more important. Okay, but it would work out the same. All right, so let me just see. I'm just quickly thinking about something. Um, hmm, but logically, to me, I would say it would make more sense to swap our ranking table around. I'll go think about it and play around and then let you go if the min problem will be literally exactly the same, like from start to end. Then I'll let you know. I don't normally ask them, and I'm just saying if we do, then I'll just let you know exactly what to work with, because my logic is saying something must be different, but I'll let you know. But the thing that is definitely different is the fact that instead of when we get to the stage of checking our constraints, we're going to check greater than instead of less than, and when we put in our Z, we're going to look for the minimum instead of the maximum. Right, but obviously just want to erase all of this. That is not what we're focusing for now because a knapsack is most likely a max problem where you want to maximize the worth and your constraint is going to be the what you put in, so some limitation to what you can put in. Right, so your Z over your constraint, don't swap them for a max problem. I'll still confirm with the min to make sure. I don't want to promise yet, but don't swap them for a max. It must be Z over C. Must be. You saw now me playing around with value saying if your Z is larger than the constraint, it tells me that the worth of this item is much more. If your Z is smaller than your constraint, it tells me that my worth is much less and my limitation, or not the value for the limitation, is not that great because it's going to probably be much larger in terms of the limitation of just 15 that I want there, just to write it again. Right, so always Z over C for a max problem. And we're focusing on max for now. So now we go and say, but how do I make this table? So you literally have to go and say Z over C for literally X, all the X variables, and then we're going to rank them from largest to smallest. So I'm not going to go and do that for you. You can see there that it's literally going to be the specific X over the specific X. So X1 is going to be 4 over 12. X2 is going to be 2 over 2. X3 is going to be 2 over 1. X4 is going to be 1 over 1. X5 is going to be 10 over 4. Just be careful to read the instructions on assessment Q because in a lot of cases we prefer to see the fraction as is so that I can see exactly what did you use. Because if you now go and say 4 over 12, isn't 4 over 12 able to simplify and make it smaller, which is still the same value? What would it be? 1 over 3. Right, so even though it's the same value, I cannot for certain say you used 4 over 12 and not something else. Right, so you could have used, I don't know, 2 over 6. And then I'm like, that's not correct, but I don't know because you used 1 over 3. So read very carefully what do we want. If we want the simplified ones, then go and use your calculator and give me 1 over 3. If we say leave it as is, don't simplify 4 over 12. If I want a decimal, well, there you go. Read significant figures or decimal places, but read very carefully. Right. You don't want to miss marks just because of an instruction, because we want to see something specific. Because there's reasons for the instructions. We're not being funny. I told you that before. Right. Right. Anika, very good question. I'm going to get to that just now. All right, so we go and you say Z over C for each one of them. And I told you we go from largest to smallest. Okay, let's go. So we say, okay. Um, sorry, I was just thinking. And largest to smallest, so the largest value is there, the 2.5. So that's our first choice if we start doing the branching. Second choice would then be the 2 there, second choice. But now, before we get to the 0.33, we have two of the same values here. Technically, it does not matter, but we follow the same standard due to obviously you filling in on assessment queue, and it's going to change a lot of things if we do not follow the same standard. Right, and obviously then you make sure that every time you solve, you're following the same standard so that it can't force you to maybe branch something twice because by accident you now swap. Right, so we always go like we normally do. Yes, Anika, we always go with the smaller subscript between the two. So x2 would have been our next one, and then after that, this one. So perfect. Okay, and then the 0.33 is the smallest value, so that's our last value that we will look at. So this is our ranking start. It's something you have to continuously use. So it's very important that you have this ranking table. I'm just going to write it out. I'm not saying anything, I'm just writing it out. Whoops. Why did I go 5, 3? Oh, but 5, 3, 2, 4, 1. But those values are very important for me to know why did you rank it that way. Okay. All right, now we can start. I'll pause every minute, every now and then, just to make sure that you're still with me and you didn't disappear. So I'm gonna just ask you a favor every now and then. If I didn't ask you something for a while, just give me a shout that it's still okay, that we're still going. Thank you, Danilo. That we're still going and it's still okay. All right, cool. So ranking table, very important. Every now and then we're gonna come back to it. All right. Um, yeah, let's get to it. So I'm gonna start it. I'm gonna show you maybe in like 2 or so branches. Then I'm gonna first ask you to try and complete it, and then I'm going to come back and do the rest just to see if you get the idea. Then obviously the exercises you can do. Right, but let's start and let's get into it so you can see how it works. But always Z over C, it's a max problem, most likely, and you need a ranking table. Now, this ranking table helps you not to pivot things again and again because you forgot about it. Okay, that you already had it in your combination in it, for an example. Right, so it's just steps, and you follow the steps and you'll get the solutions without having double of them. So, which one is the best in my table, the best rank? You can guess. What's my best rank for ratio? X5. So X5 is our choice, if we can say it like that, to start with. Not to branch. Please don't go and say X5 is this and X5. No, X5 is where I start. Okay, so you need like a calculator handy now to do the calculations. So have a calculator ready. Let me give you just a minute to get one if you're like, I don't have one. Maybe I should also get mine. Just give me 2 minutes, just to make sure that I can double check that we don't make any mistakes. Okay, I've got mine. I hope you got yours. Calculator to help us do it quickly. Someone just quickly asking about. Just want to open this quickly. I'm gonna be with you in a minute. Okay, I'm ready. Just wanted to help someone quickly. All right, let's see. Where was I? Where's my journal? There we go. All right, so yes, we're going to start with using our ranking table. So we start with the largest value every time. We work with the ranking table largest to smallest. And yes, we eventually find branches that we're then going to create sub problems and branch and branch and branch. Yes, let's get to it. So our biggest one is X5, or our best rank there is X5. So we're going to start with that one. Now you have to constantly check your constraints and your Z when you actually get a possible candidate. All right, so I'm just going to erase this so it looks a little bit better. That 15 is fine. Just by accident erase the value as well. 2. Okay, so that's a 2 there. That's good. Okay. So we start with um, let's start with X5. So obviously in the test you'll see there we don't give away the fact that you check X5 first. I mean we give it in form of X1, X2, X3, X4, X5, blah 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 blah. To not give away that you should actually be using this ranking table. I mean you should know you should be using it. So in this ranking table we check X5 is the largest, so that's what I try to put in first. Now if I choose this I one. So if we choose it, now my question to you, my constraint has a limit of 15 kilograms. Will this go over my limit of 15? Good. Uh, it will not go over the limit. Your limit is 15. Danilo, can you guys hear me still? Cool. Okay, let's see. We place that item. It will not go over. So basically what I'm saying is I can make x5 equals to 1, meaning I can put it in the bag because it doesn't go over my constraint. So if we now do the calculation, we literally go and say, out of the 15, if I put this x5 item in my bag, I'm going to be left with what? So you guys tell me, what do I minus and what am I going to be left? Perfect. So 15 minus the 4 of x5, and that gives us an answer of 11. Very good. So we have 11 left for next items that we place. Okay, so now we get to it. What's the next item I then want to try and place? Look at your ranking table. X3. Yes, we go now with X3. If I make X3 a 1, Would it be possible with what I have left? I'm wondering, good. X3 has a constraint value of literally 1, so I can put it in. I have 11 left, but I want to put this in. Then it's a value of 1 in terms of kilograms. So yes, I can. So I say, yeah, put it in. So we're going to have 11 minus that 1, which gives us a value of 10. Perfect. I expected the values to be worse. We don't need a calculator. But anyway. Now, what's the next item that we're going to go with? Looking at our ranking table, we now go with x2, yes. x2. x2 needs a value of 2. Do I have enough left to put that in? Yes. So I put it in, and I say from the 10 that I had left, I now use 2 of that. I'm left with 8. Thank you. What's the next item? You'll see I usually make some stars or something to keep track. x4. So x4 is our next item. Do I have enough to put x4 in? Yep. x4 is just a 1. So out of 8, I can use that. Yes. So out of 8, I put it in, and I'm left with 7. Now we only have 1 left. x1. But do I have enough left to be able to put x1 in? No. So I'm just going to, if you're like, what is she saying? We have 7 left. x1 needs 12. No. Right. So here, I am not going to put x1 in. However, because I can already see what my problem, hint, hints are problems, what my problem is, I want to write it in form of a fraction so that I can see what is left over what is actually going to be needed. Right, so to give me a value between 0 or 1. So guys, quickly, if I look at what is left, what was the amount that's left? 7. What is the amount I need to put x2 in? What is the amount that x2 needs in terms of kilograms? Or what's the amount of kilograms for x1? 12. So you always write it in terms of what's left over what it needs. x1. Did I say x2 by accident? If I did, sorry. Let's continue. x1. Right, so just to make it clear, you're not saying 12 over 7. What's the answer of 12 over 7? Quickly tell me. What's the answer of 12 over 7? You can round to like 2 decimal places. 12 over 7. What's that answer? Is 1.71 between 0 or 1? Because these are binary values. Is it between 0 and 1? No, so please do not give it to me like that. It must be the leftover over the amount it actually needs. So meaning it needs, it's going to be a value of 12, but I only have 7 left to place. So write it in that form, and that's 7 over 12. What's the value, even though we don't write it as a decimal normally? What's the value? 2 decimal places. Say approximately. 0.58. That's between 0 and 1. So that's the purpose of showing I'm going to draw this in between. So I'm either going to go 0 or 1. And why do I do that? Because it's binary. Right, so this final answer, please, must be what's left over what do you need to use for that value. So meaning what's left over the constraint value. I just keep on saying what you need to use because I'm used to like, oh, we need to still put it in the bag. Right. If there was any x variable that you didn't get to, that x variable will then be equals to 0 because you never got to that item, so it's not in the bag. So just to make it clear, we don't have one, but just to make it clear. Now, who can guess what are we going to do with this x1? Who can guess? It's a value between 0 and 1. What are we going to do? Two sub-problems. Yes, branch and bound. So we're going to have sub-problem 1. I'm going to say sub-P. Sub-problem 1 and sub-problem 2. On the one side, we're going to focus on making that specific x, which is x1, 0. And on the other side, we're going to make that specific x a 1. So here's there's no less than or greater than. It's purely just saying I either make it a 0 or a 1. But I did warn you on branch amount simplex, we do the less than and greater than or equals to root. Less than or equals to and greater than or equals to root. But with this, it's literally equals. Either this or this. Now, guys, it doesn't matter if subproblem 1 is x1 equals 1 and subproblem 2 is x1 equals 0. Just swap. You just have to make sure on assessment queue you follow. So if I said 1 is going to give me a candidate, then you quickly solve them and tell me which one. And then you fill in those ones' details. So I'm just giving you some advice, right? Because we don't want to give away the answers. So let's see. Let's see if we will even get a candidate. Let's see. So now we do branch and bound, but there's a little bit of a trick to it. So I just want to do this one with you so that you can see what trick I'm talking about, and then you'll be able to do the rest. So let's start with subproblem 1. Now it's subproblem 1. So I always do something like this. Let me just first erase those because we're going to use it again. And then when I start writing it, I do something like this where I say, okay, I'm going to use a different color. X1 equals 0. And then I put like something like a little star for myself so that if I continue branching on this one, I do not forget that X1 is equals to 0. It says X1 equals 0 when I branch from subproblem 1. Because that's where I made it, I keep on making it that. Got that? You guys still with me? Just want to double check. Cool. Okay, so I just wanted to check something before we continue. Guys, please don't forget about this Excel sheet that you need to go through with the logical constraints to help you. And then just check there that, where's that one? When we say either or, we have options due to some people being able to argue the fact, but normally when we say either or, we literally mean either this one or that one, nothing else. So I just want to highlight this one for you. You can take a picture. We prefer this because if you say either or, you necessarily don't refer to them both being possible. You're saying it's either this or this, nothing else. Not both, not none. It's either this or this. So it's either the one or the other, nothing else. Okay, so just want to make it clear. Cool. Just wanted to make that clear before I forget about it. Right, so just take a picture of that so that you know we prefer that either or instead of the other one where we're saying both are allowed. We don't prefer that. Because if you say either or, you literally say it's either this or that. That like there's no like having them both or none. Just want to make that clear. Cool. Okay, can you guys hear me? We good? We're ready to go? Ready to do this? Or are you still okay? Well, maybe not okay, but with the work. Just kidding. I hope you're okay, but with the work as well. Okay, let's see. X1, I'm making a note there to just keep going. If I continue branching on this one, X1 is going to be 0 for problem 1 specifically, if I branch from problem 1. So 0, that's where I start. Now, the next step, as soon as I'm done with that one that I'm branching on, I immediately go check my ranking table. What was the first item that we should use in our ranking table other than X1? We're not looking at X1 at all because it's done. It's already placed. X5. Okay, we go X5. Put it in the bag because we know out of 15 it only uses 4 and there's 11 left. What's the next one? X5, you got your ranking table, it's the largest. So that's the one that you're going to put in next. You have out of your constraint 15, still 15 left because x1 was equals to 0. So you're not placing x1, so it doesn't take up any space or kilograms. So you still have that 15 for your constraint. Then you go check, okay, what's the amount of kilograms for x5? X5 is a 4. So I go and say out of this 15, it's going to use 4 kilograms out of that 15, and 11 is left for the next item. Go back to your ranking table. What's the next item? You guys already gave it to me. So the next item is then going to be in my rank, number 2, which is item 3, x3. So I go for x3 and I say, before I place it, do I have enough left? So I check, I've got 11 left. I go check in my constraint, how many kilograms do I need for x3? X3 only needs 1 kilogram. So it does have enough space for that. So I'm going to put it in the bag. So out of 11 that was left, I used that 1 kilogram and I'm left with 10 kilograms. Then we go back to our ranking table. So ranking table, the next item is the third one, which is X2. So I go and check X2. I have 10 left. So just to highlight again, I have 10 left. Now I go back and I check the kilogram. 2. I do have enough place for it. So I go put it in the bag and I say out of 10, I'm placing 2 kilograms, which leaves me with an 8. Then I go back to my ranking table and I see X4 is the next item. So I go and say X4, I'm going to write it here at the bottom. X4, then I go check, I have 8 left. How much do I need in terms of kilograms? Do I have enough? Yeah, out of 8, I can place 1 kilogram, definitely. So 8 minus 1 equals 7. Do I have any items left after that? Technically x1, but I told you we forced x1 to be 0. So you're not going to go and try and do it again. It's already 0, definite. So what do you guys think? Should we branch on this one further? Is it a candidate? Is it infeasible? What do you think? What you're thinking there? Candidate, yes. So we're going to go and say this is a candidate, right? Why is it candidate? Because the items we said is equals to 1, do not go over the limitation we have, and we forced x1 to be 0, but that's not a problem. It's just one possibility. Right. Yes, Armando, you don't subtract the value because it's not being placed in the bag. If you say it's equals to 0, it's not actually being placed in the bag. So there's no need to subtract that amount of kilogram if it's not going to be placed in. And if it's a 1, you subtract because it's going to be placed in the bag. Right. So the specific x1's value, for example, if it's a 1, that value comes from the constraint because you're checking the constraint constantly to make sure that you don't go over that limitation. Right. So if you had space, Caitlin, if you had space left over after everything was placed and not placed, obviously you still have to do the branching, what. But if everything was placed and the things that were forced not to place, and there's no fractions that you have to branch on, and you still have left over, then it's still a candidate, yes. Okay, so even if you have space left over, it's a candidate. It's only if you have space left over and you haven't tried putting something in that still needs to be put in, if it could, you still need to continue. So it's only if you literally have no fractions where we had by the previous one where we could have placed x1, but we didn't have enough, so we made a fraction. So if that was not there like this one, it's a candidate, even if there's some left. All right. So here we still have 7 left, but we don't have any more items. So this is going to be candidate A, for example. Right. Cool. So how do we get the Z value? What do you guess? Like you can give me the Z value if you can guess. I'm going to scroll. Remember, it's only x1 that's 0. It's only x1 that is 0. All right, cool. That's very good. So you go and now check the actual Z values. You're talking about the best Z value. This is a max problem. So you want the best Z value. So you go substitute the ones and the zeros into your Z to check what's the Z value for that candidate. So even though you can do this quickly, x1 is a 0, x2 is a 1, that's a 1, that's a 1, and that's a 1. So you've got literally 0 plus 2 plus 2 plus a 1 plus a 10. And that gives you the Z value of this specific candidate, which is then 15. Very good. So we then go specify so that when we come back, we know exactly that the value of this was actually 15. Don't know if it's correct yet or the best yet, but that's pretty much it. But now we go and do subproblem 2. So let's have a look at subproblem 2. Start with the one that you're forcing, or if you had more than one forcing, you would do that. But let's try it. Okay. So let's see. Subproblem 2, we're forcing x1 to be equals to 1. So we go and say, okay, x1 equals 1. So if I'm going to, so just to make it clear, if I'm going to branch on problem 2 further, x1 stays 1. x1 stays equals 1. Let me rather say it like that. Because if you force it from the 1 and you continue from that branch, so if I were to continue from problem 2 and I make it 2.1 and the problem 2.2, that x1 stays equals 1 because I'm branching from, I'm building on this problem. So when you build on a problem, just like branch and bound simplex, you copy that table. So meaning whatever I forced before, I keep on forcing from that branch. Otherwise, you're going to be doing stuff over and over. Right. So just to make it clear, that's what we're technically doing. But let's have a look. So x1 is my constraint limitation. It is, I'm just going to highlight again, a value of 15. I'm not going to just use yellow or something. It's a value of 15. Do I have enough kilograms for x1 to be in the bag? Yes, x1 requires kilograms of 12. It's heavy, but it can go in. So we're going to go and say, okay, it can go in, and I'm forcing it to go in. Now, quick question, make it equals 1. Remember, we said on this side we make x1 0, on this side we make it 1. So meaning I make it 1. I'm not asking can it be 1. I'm making it 1. If x1 had a value of 16 kilograms, what would I do? What do you guys think? Would I continue branching? Will I say it is feasible candidate, or will I say infeasible? Thank you, Caitlin, and probably Rishka. I see Rishka, you were typing. Infeasible. Right. So if you say that it must be 1, and it can't, and it can't, then you know definitely it's infeasible. So just to make it clear. Okay, because you're saying it must be 1. Now I'm like, but it can't go in. Then it's just an infeasible solution, right? It's not actually something we can use. Okay, but it's not true for this one, of course. I just said what if, so you know for future branches. So we put it in and we say, okay, out of the 15, we're going to use 12. What's left? 3. Right. Okay, so now we have 3 left. So your focus now is 3 is left. Okay. So if 3 is left, I go back to my ranking table. Why does it do that? I go back to my ranking table. I check. X3 is, not X3. X1 is chosen. What is next? So if X1 is already forced, I don't even look at it, no matter if it's the first or the second or the third or whatever. I don't look at it. Yeah, so we now go again. Okay, my first rank. So you'll see I normally erase this and say I'm starting again. Okay, so my first rank is this one, which is X5. Okay, X5. How much kilograms does X5 require? You guys tell me, how many kilograms does X5 require? Perfect. X5 requires 4 kilogram. Do I have enough? And Adrian. Do I have enough for that 4 kilograms? No, very good. No, 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 no. So X5, just to make it clear, requires 4 kilograms, but I only had 3 left. What do we do? What do I write? You guys should know now. What do I write? Do I write a 0, a 1, a what over what? Yes, we need to branch, but what do I write? The question mark. Okay. Even though technically you're not putting in the bag, so Caitlin, I do agree, it's technically a 0 because you're not putting in, but we want to be able to identify that this is what you're branching on. So we want to see what was left over, what does it need to know, why are we going with this one? Right, so 3 over 4 is what we require there, definitely. So 3 is what's left over the amount it requires, and X5 requires a 4. Right, and why not 4 over 3? I told you from the beginning, if you do it the other way around, it's not necessarily going to be a value between 0 and 1. So it must be the leftovers over what is required. Right. And this one is not infeasible. It is only infeasible if you're saying I'm branching on this. So basically I'm saying x1 must be equals to 1. So if I said it must be 1 and it can't be a 1, so I don't have enough space for it, then it's infeasible. In this case, I had enough space for it. I also had enough space for others. I just don't know what yet. But x5 I don't have enough space for. So I say there what is left over what is needed. And now, yes, we're going to continue branching from this one, right? But it's going to now branch from this one. But if your x1 was, for example, yes, so where I made it, for example, a 16, and I said x1 equals 1 is what I'm branching, then I'm basically saying it must be put in the bag. But if it's 16 and I only have 15 kilograms available, so my back is going to break if I put a 16, then I cannot do it. And I say immediately infeasible and I can stop. But because there was space, we could continue. All right. So yes, yes, yes. Awesome. All right. So branch immediately. So yes, Caitlin, you're not even going to go and say, oh, x2, x3. No, no, no. There's no space for anything other than what we have currently and what we're checking currently. So right now, so just to make it clear what Caitlin means there, x2, I'm not putting in the bag. x3, I'm not putting in the bag. x4, I'm not putting in the bag because we didn't even get to those items. We put x1 and then we tried to put x5 and we saw, oh, okay, can't do that. So the rest are definitely not placed in the bag. So you go right there that they are 0 to make it clear that we're not even looking at them right now. If we force them to be 0 from a previous branch, well, then still 0. Okay, because we have to know that you know how to show. So in this case, the x5 is a fraction because we're branching on it, and it shows me how much was left over what is required. But the rest, if I don't place it, they are zeros. Right, so just to make it very clear. So now you'll see what I'm going to mean with, okay, we keep on doing this branching, forcing thing. So at problem 2, we forced x1 to be 1. So when we get to problem 2.1 and 2.2, x1 equals 1 stays x1 equals 1. You don't go to x1 equals 0 because that's a different problem. That's problem 1, not problem 2. But I keep on forcing it. I'm not going to check again if it's going to be 0 or a 1. No, I keep on forcing x1 equals 1. What is new, though? You can tell me what's new for problem 2.1 and 2.2. What am I forcing now? Now we are forcing x5. So for the one, we're forcing x5 equals 0. For the other one, we're forcing x5 equals 1. Remember, I told you you can swap them around. This could have been the one, the other one is 0. Just check on assessment queue. Am I asking and saying one is a candidate? Then you specify which one in the correct blocks, obviously, and what is there. All right, be careful. But now x5 is a focus. So now you'll put a little star there to say, that's now what's being forced in this case. Right. Liam, what order do you mean? Do you mean the ranking? Do you mean the order that we write it? Like, what order do you mean there? Because you're still gonna fill it in from x1 to 5. You just have to fill in the correct stuff at those. But you continuously use a ranking table if it's not forced. And I guess that's what you mean. And no, x1 and x5, but x5 goes first now. So whatever you're forcing is saying it's a must. That's why I said if I say it's a must and it doesn't make sense, then it's infeasible. So whatever you're forcing from a branch, or even from previous branches, it's still being forced. So it's a must. So whether you start like guessing you looked at problem 2.2 and you were like, so at 2.2, it doesn't matter if you start with x5 or x1. If you try to put them both, it's either or not going to work. But what you're forcing is what you're forcing. That goes first, definitely, yes. So that you check first, and then only if there's anything left, you go check your ranking table. But if you force it and you see it's not possible from the start, like I gave that example, infeasible. So let me ask you, which one is infeasible, even though I technically said it, but you didn't hear me. Okay. Which one is infeasible? Thank you. 2.2. All right, we can see from above that if we put x1 equals 1 and x5, we tried to put x5 didn't have, I'm going to say there was not enough kilograms available for us to put for. So if we then say, but it must be a 1, it's going to be infeasible because it's not possible. Right. So you can technically immediately, without doing any calculations, go and say, this is infeasible. No. Just to make it clear, if someone's not sure, guys, if you put x1, you go check. It doesn't matter if you start with x1 or x5, they're both being forced. So if I go back out of 15, which is my constraint value, x1 requires kilograms of 12. So you go and say, okay, 15 minus the 12, it's going to give me a 3. Then I go check x5 and I say I've got 3 left, but x5 requires 4. It's going to give me a negative 1. No. So it means I don't have enough space to put those two in, but I said I must put them in, so it's infeasible. Right. 2.1. What's happening there? Who can tell me? Are we branching from it? Who tried? Let's see who's correct. Okay, so let's start with x1 equals 1. So that's a 15 minus 12 equals 3. We already know that. x5 is equals 0, so you don't subtract anything. Now, when I go to my ranking table, which two variables am I not going to look at? Which two variables am I not going to look at? x1 and x5, perfect, because they're forced. So there's no looking at them. Right, so you can have a pen and a pencil and paper to just like erase and cross and erase just to help keep track. So we go and we say, okay, what's then next in my ranking table? What do I go with next? X3, perfect. So in our ranking table, this would have been next. So we go with X3. How many kilograms do we need for X3? 1, perfect. I'm just going to go and erase some stuff there. We need only 1. Okay, we only need 1. All right, so let's go see. So we say if it's equals to 1, it's only going to use 1 out of the 3 that's left. So just want to make sure it's x3. Okay, now I have 2 left. What's the next x item that we can use? The next x. X2, perfect. Now we go with x2. How many kilograms does x2 need? 2. Okay. Now is the question. Now we see who's correct because this is a quite interesting one. So if x2, if I put it in the bag, what's left? Nothing. So if I now go check what items are left, we had 2, 3, 5, 1, x4. So if you were to continue, it will be unnecessary. So technically, you could have gone and said I have 0 left over. What do I need for x4? So x4 needs a 1. But 0 over anything is going to be 0. But It doesn't matter if you continue. So what's going to happen is this is, let's say you say now this is candidate B, and you continue. And you said, let me not do that. So your one is going to give you candidate B, and your other one is going to be infeasible. So you could have stopped immediately and said, well, that's pointless to say that the other one is infeasible. It's on the dot, nothing's left. If it's on the dot that nothing's left, then the next item is not going to be a fraction because 0 over anything is anyway 0. You can remember it like that. 0 over anything is anyway 0. So 0 is going to be the answer there. Right. So this is going to be candidate B. Perfect. And then, so you're saying if you went and said x4 equals 0 and x1, it would just be a waste of time. You can, it's just a waste of time. So you can immediately say this is candidate B because 0 over anything is 0, so it's anyway going to be a candidate or infeasible. It's not going to continue branching because there's nothing left to be able to continue branching. Right. Okay, let's remember which x values are 1. So it's 2, 3, and 1. 1, 2, and 3. Oh, so original. Hey. 1, 2, and 3. So let's go back here. What's our z value? 1, 2, and 3. What's our z value? Perfect. 8. Our z value is 8. So here our z is 8. It is a max problem. So which one is the best out of CA and CB? A. Perfect. And there we go. That's our best answer. I expected this one to be longer. That's why I said you'll do some of it, but apparently it was very short. So you'll do an exercise instead. Okay. I was expecting it to branch further, then I saw the 0. I'm like, oh, okay, never mind. Usually we do, yeah, usually it's much longer than this. You probably already saw your assignment. It's not this short. Okay. It's not too long. I'm just saying it's not this short. All right. Okay, but let's take a quick break first. So let's make it until 20 past, and then we first do some of the fixed charge exercises, and then I'll decide where we go from there. All right, so let's be back. Okay, I'll give you a bit more time, but back at 10:20. We'll see the screen. Just putting the headphones closer, but yeah. Hey, awesome. All right. So that's the idea of knapsacks. So whatever you branch, you continue branching. So you'll see there, just to draw it out, that when you continued from this one, because you branched on x1 equals 1 before, you actually continue making x1 equals 1 for all of those from that branch. Let's say candidate B was not actually a candidate, and you had to make subproblem 2.1.1 and subproblem 2.1.2. You would continue doing x1 equals 1 for both. What else would stay the same for both? x5. Perfect. x5 would stay 0 for both because we said it's 0 from this specific branch. And then whatever item you would have branched then, you would have then gone and did a 0 and a 1 for whatever one you would have done there. Okay. That's the idea. Of course, do the exercise. I just want to go and recap some of the other work. So I'm going to close this. So remember to go to this Excel sheet and have a kind of a generalized form of how to write some of those logical constraints. Traveling salesperson is next week, so you don't have to worry about this yet. Okay, fixed charge. I wanted to focus on that one constraint, and then we'll have a look at something else. Let me just open this. Okay, so from the fixed charge one, and most of it was fairly simple, except this. Right. So just to make it clear, you would have set it up like you normally do. What's the constraint? What's the objective? Um, so let me see if I do have that answer somewhere. So there's the IP without that. So it's a normal, you're going to have X variables, which is the amount of that product that's being sold, and your Y variables, which is the setup cost for that product, which is either going to be paid or not, depending on whether the product is produced or not. Then you had your objective function in terms of the actual, what was it? Let's see, profit. So you'll see the product one has a profit of $2 per unit, product two has a profit of $5 per unit. Now be careful if there were costs specifically for, let's say, product one, you would subtract it from the profit because you always say revenue minus costs to get the profit. But these costs were once off setup costs. So they are not going to be subtracted from the variables. So if X1 is the amount of product one and X2 is the amount of product two, and you set up your objective function, you're not going to have some value of X1 being subtracted in terms of that cost, because that cost is once off. It's not for every single value in terms of that variable. So it's not if X1 was equals to 10, it's not for every single value up to 10. Right, so setup costs or fixed costs, as you know it by now, is Y variables, which is just binary that you work with. So that's where those come from. Then you have to think, am I going to add or subtract them in my objective? In my objective, I'm dealing with maximizing profits. So revenue minus costs. So I'm going to subtract the Y's for that. Okay, so just to make it clear where that comes from. Then your constraint, and then you set up your linking constraints. These are the linking constraints where you had to get the max value and use that formula of xi less than or equals to some max value for that specific item and which setup cost or machine or whatever is being used for that. So maybe x1 is for 1, and then you set it up like that. But my focus is going to be on what if we change it. So the one that I highlighted there where I said change the IP so that product 1 and product 2 uses the same set of costs of $40. So if they're going to be using the same setup cost, then some of you would immediately go and say, oh, okay, 40y1 and 40y2. Now, that would work if, let's say, you're going to pay it twice. I'm hoping you hear what I'm saying. So meaning, if I were to make units of product 1 and I pay $40, and then I make unit 2 or products of units of product 2, and I'm going to pay another 40. So meaning I'm going to have basically, if I put it in terms of machines, 2 machines. In this case, it's 2 setup costs, right? But if it's the same setup cost, meaning if I make either product 1 or product 2, it doesn't matter, it's going to cost me just a value of 40, then I'm only going to have one Y for that. So it's, how can I say, you have to think about it a bit to say, okay, is it going to then be for both, or are they both going to have separate $40? So just to make it clear, if they're going to both have $40 each, so meaning the value of 40 applies to both, but it's not the same setup, then you'll have it as 40Y1 plus 40Y2 and do it like you normally do. But if, like in this case, we're saying the same setup cost, so we're basically referring to the fact that they both, whether you make the one or the other, the setup is going to be $40, not 40 times 2. So it's going to be $40. So in that case, you're going to have only one Y specifically for both of them. So Y1 is going to be for product 1 as well as product 2. If you do both of them, it's still just $40, not 80. Right, so that was what we're trying to do here. And then I want to show you, but how do we actually work with that? So of course, that makes it only one Y1 instead of two Ys. Sorry. Let me just, oh, I gave you some extra examples here about what if it's more, what if it's should be less than this. Those are quite nice to do. I didn't put that one in. No. Okay, so let me show you how to do that one. Probably why you guys are asking. And let's go here. So let me just zoom. Scroll down. I'm zoomed in. Okay, so we're basically saying we're taking the same IP. So it's still the number of units product. X1 is specifically for units of product 1, where X2 is specifically units of product 2. We now only have one Y. That's the setup cost for both in this case. Then our max Z is still going to be 2x1 plus 5x2, but it's now $40 for them both. But just like I explained, if it's $40 for each, it's just the same value, then you'll have a Y1 and a Y2. But if it's $40 for both of them, then it's only going to be one Y that's going to take care of both of them. So whether it's product 1 that you make or product 2 or both, just going to have one setup cost. All right. Yes, it's always the wording. Now we go and we say, okay, what about the constraints? So our first constraint still stays the 3x1 plus 6x2. That's the constraint that you guys normally would have worked with. So I'm not going to work with that, tell you about that constraint. Now the linking. So that's where you guys probably were like, what now? So the linking constraint. So, whoopsie. They are now using the same setup cost, so the same Y. So to link them, we have to include them both. If they were using separate Ys, we do it like we used to do, where each of them will have an x1 less than or equals to some max value y1, x2 less than or equals to some max value y2, max value for x1 here, and the max value for x2 here. But because now we have a setup cost that is for both of them, we are going to make sure that our constraint is actually for both of them. So we include them both, and then we do that whole less than or equals to max value, and that specific setup cost or machine or whatever fixed cost is to do with both of them. So now you're going to say, okay, but how do I get that max value? Right, so let's have a look. So to get the max value, you know by now you should be using your constraints, right? So let's quickly get the max value for x1 and the max value for x2. So you do it like you normally do if you had more constraints, let's say, I'm going to say e.g., please, it's not part of this example. Let's say I had another one, but this way around. Very, very creative. Let's say quickly the M for x1. So for x1, what's the max value if we look at this one, the one where I put the star? Or what over what? What's the max value for x1? But yes, Amandre, you would then go and say 120 divided by 3 is 40. So it's the one will be 0 to get the max of what the other one could be. So it would be 120 over 3. So I'm just going to undo that so that I can remove the 0 there. But the max would be 120 over 3, which is 40. Then we check, what about the max for this EG constraint? You can tell me what's the max for the EG constraint, or the extra one that you don't have, just to make sure that the topic is clear. What's the max value for that one? Give you 20. Now, from what we did yesterday, which one would I say should we choose for a max? Just to recap. So if we say 40, yeah, for constraint 1, 40 is allowed, but can we make 40 if we look at constraint 2? No. So you pick the smallest. All right, so the smallest, because you're basically saying due to constraint 2, I can't make 40 at all. So the max is actually 20. Right, so in our case, it's going to be then 20 that I use. If I were to look at M for x2, let's quickly look at my first one. That would be 120 over 6, which is 20. And the other one would be 120 over 3, which is 40. In that case, again, the smallest one, because we're then dealing with, obviously, sorry, I'm a bit cold. Obviously, the smallest, but due to the fact that you are saying the other constraint cannot allow you to make more than that amount. So between more than one constraint, if you're checking the max, I'm just saying between two constraints, if you're comparing the max value, you take the smallest, because the constraint that has the smallest value is saying it can't go more than that. So whether the other constraint is allowing more, this constraint cannot go more. Right, yes. So if you have multiple constraints, you'll choose the smallest value for that. Right, but now going back to, but how do I get the max between two variables? Right, so I'm going to just go and say, okay, this was all in EG, so I'm going to go and say, okay, that was just if we had that. Right. Now let's go back to constraint. So let's now go, probably use a different color. So I'll go now with this constraint. So getting the max for x1 is simply saying 120 over 3, which is 40. the max for x, which is going to be 20. So we've got our two values that we can compare. Now here you don't choose the smallest. Okay, so I'm going to explain the concept now. I just want to give you a minute if you wanted to take a picture because I'm going to be erasing the crosses there. Okay, you guys good? Before I erase? Just give me a thumbs down if you're still busy, but I'm going to erase if no one gives a thumbs down. 3, 2, 1, and gone. So only between two constraints is the smallest one, but we're now comparing to two different variables to get the max between two variables. Sorry for my ugly arrows there. Imagine they're very pretty. Okay, there we go. All right, so between the two, so we've got a max for x1 of 40 and a max for x2 of 20. Now, we want the max of both. Well, I basically gave the answer now, but to explain, if I only choose to make x1, only, if I only choose to make x1, if that's the solution, only x1, then x2 will be 0. And I'm going to get the max amount for left over, if that makes sense. So whatever this is, it's going to be the maximum amount it could be. Right. And what's the max for that one? Oh, it is 40. Okay. Now I say, but what if x1 is 0? Then I'll get a max of x2, which is 20. But do I know for certain that x1 would be 0 or x2 would be 0? Do I know for certain? Well, I'm already saying no because I'm saying or. But do I know for certain? I don't know the answers, right? I do not know the answers. Okay. Go more than 20. If x2 is 0, x1 cannot go more than 40. But as soon as x2, so just to show you, x2, as soon as it increases, x4 is going to decrease because you can't have that max amount if you start then also making x2. So as you, let's say, you say this is not 40, that's 0. Now you say, no, okay, let's make 10 of this. Then x1 cannot use its full amount or its full capacity. So maybe a 30. I'm not giving the correct answers, but maybe a 30. So if I do that, and I tell you we do not know the answers, what max amount am I going to use? Am I going to use 40 or 20? I do not know the answers. I cannot restrict too much because I do not know the answers. I do not know if x2 is going to be more. I do not know if x1 is going to be more. So what's the max value? We've got a 50-50 shot here, hey? It's either 20 or 40. Between two constraints, you'll take the lower. Okay, between two constraints, you'll take the lower because the other constraint cannot make that amount. Right? So between two constraints, that's a yes. But between two variables, that's a no. Between two variables, you're going to take literally the max amount. And the reason being is I do not know what the answers are going to be for x1 and x2. So it's not that they can't be that amount. So it's not that I cannot have a 4G and a 0. I can. I don't know. That's possible. Why can it not be? There's no constraint saying I can't go more than 40 for x1. There's also no constraint that says I can't have 20 and 0. There's no constraint saying I can't have a 30 and a 10. So when it comes to between two variables, so between two variables, you take the max value or largest, if you want to remember it that way. Yes, it's just because we're using the same two machines or the same setup cost for them both. Then you have only one Y for them both. If, let's say, it's just the same value for them both, but they each require to get that setup cost. So let's say if I make product 1 and it has a setup cost of 40, and I make product 2 and it has its own setup cost for 40, then it's going to be 40 plus 40. Then I need Y1 and Y2. But in this case, we said the setup cost is 40. No matter if you have product 1, product 2, or both, it doesn't matter. It's just going to be one single setup cost. So then it's only one Y that you're using for both of them. Right? So only one Y. So in this case, Y needs to change to a 1. Amanda, I don't know what you mean there with the optimal table won't change since y1 is equals 0. That's what this constraint is for. But x1 plus x2 less than x2 my1 is to set it up to make it change to x1 and x2 on its own because they're using the same setup or the same machine, if that makes it sound a little bit easier to understand. Y1 should not be 0 if you have your linking constraint. If you don't have your linking constraint, then it will be 0. But you need this linking constraint to make it a 1. So if I now go and say, let's say x1 is 0 plus 0 less than or equals to the 40, because we're going to write it as x1 plus x2 less than or equals to 40, y1. So if I go and do that, 0 less than or equals to 40 times 0 is true, so the machine is not used or the setup cost is not paid. That's perfect. Now we're going to say, but what if I make 10 of this one and 0 of this one? Doesn't really matter. And I go and I use a 0 for y1. Then it's going to be 10 less than or equals to 0, which is false. So it's going to change our y1 to literally a 1. So you're going to pay that setup cost. That's purely if you have this constraint in. You need to get a 1 for y1. Otherwise, something is wrong with Excel Solver, or you didn't include that new constraint. So here, they were split up. So it was not the same cost. That was an additional one. It's not the original question. It's an additional bullet point. So it changes this. So when you do this one that I have now, you're only going to have y1, not y2, and y1 must actually be a 1. There's no choice because both of them use the same set of cost, and you're actually going to make something. So it's going to be a 1. Well, it needs to be, otherwise your linking constraint is not doing what it's supposed to do, because it's there to make sure that you pay for it. Just give me quickly 5 minutes. I just want to quickly run out. Just give me 5 minutes, and then Armandra, you're getting a chance to redo that quickly. Okay, sorry for that. Armandra, any luck? Yes. Okay. Right. But the whole purpose of that constraint is to make sure that y changes to a 1. Right. Let me just go back here. So the rest will stay the same. It's just to change it to 1. Just make sure you said that it's a max problem. Otherwise, it will probably not do anything at all. And everything else is set up. Right. So I hope that for you makes sense. So remember, if it's between two constraints, you take the smallest, but between two variables, you'll take the largest value of them. Right. Okay, let's see. That was it for the fixed charge. I just want to go back and use this. So this part about adding the following, let me just erase this one. If product 1 is produced, more than 20 should be produced or less than 5. So the 1 is product 1. You've got an either or here. Why is it either or? So you're either going to produce less than or equals to 5. Remember, we don't work with less than. It must be less than or equals to. If you want to be very specific, you'll go 4.999999, right? If you want to be really specific. For the other one, more than 20. So you'll say x1 greater than or equals to 20. Can these two constraints happen at the same time? Let me ask you. Can they happen at the same time? No. Right? They can't happen at the same can't happen at the same time. It's infeasible if you put those two constraints in like that. It will just give you an infeasible solution because it's not possible. Right. So we have to then set up the constraints to make that possible. So that's that whole dummy constraints that we include, right? Where you use that kind of a formula. So this is where these answers come in. So you kind of use that formula where you've got some x minus a max value, but this time you're using a dummy. Do not use y because you do not want to change the setup costs variables because the dummy is just purely to work between the two constraints to accomplish that either or if then scenario. So the dummy is just purely working between these two constraints. It has nothing to do with your setup costs for your machine. Right. Then to make it also clear, so I'm just going to quickly write the whole thing here. So this one equals to the lower, just remember it's n times 2 times 2. Sorry, I forgot. It's not m anymore with these. It's upper and lower. And then you've got your upper here. Okay, so it's just those general formulas that you can use, or you can set it up by actually checking your conditions. But in this case, they're specifically referring to x1. So if I set this up, yes, it would be x1 minus, what's the upper value? They said 20. 20 times 2 is 40 with dummy 1, because this is my first dummy I'm referring to. Lower value is 5. They said less than or equals to 5. The upper, greater than or equals to 20. Okay. Then I do the same for the next one, plus 20 times 2, 40, dummy 1, less than or equals to the upper of 20. So the dummy works between these two constraints. So the dummy must have the same dummy, meaning whatever I put into dummy 1 will be put into dummy 1 in the other one as well. Okay, you can't have dummy 1 and dummy 2. That will not work because otherwise you can have a 0 here for dummy 1 and a 1 for dummy 2, and everything will be allowed. It will not do anything. Armando. So no. However, if you had another scenario for, let's say, x2, then you'll go and say x2 minus 40 dummy 2, because this is a different constraint than the constraints for x1. So this would be then minus x2 plus 40 dummy 2. So to make it clear, these dummies here for these constraints. Then for these two constraints, to get that either or, because I mean either or, I need to be checking two things. Right, either or, I'll be using the same dummy there, but not the same in between two different scenarios, if I can put it like that, or two different here, and where those formulas come from. Because everyone's quiet, so I just want to make sure that nothing's dead on my side or your side. Or thanks, Armandre and Yandre. Okay. Kind of unnecessary, but I'm going to explain them again. Obviously, do solver, test it, check what happens, what. If you wanted to make notes, now's your chance. But let me go and play around with that. Is it okay enough? Can we continue? If I need to sing a song, which I'm not going to. Unless if I go to my
microphone, maybe that might be better. How's this? Is this better? I see people typing. All right, then I'll stick to the mic. Awesome. Okay, let's just hope there's no other noises that might make it worse, but we wish for the best. Okay, so I'll quickly test it. Let's see. I'm just gonna make some space by erasing. Blah, 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 blah. Okay, so it's just to show you that if you have dummies, it's to work between two different constraints. Right, so if you have 4 different constraints, but 2 just for different scenarios, you can't be using the same dummy over and over and over. So for these 2 that work as an either or an if then, but specifically either or for this, you have dummy 1. If you then have another 2 that has also an either or what, that's then for dummy 2. If you have another 2 either or, if then what, dummy 3. So same dummy, but for that specific 2 constraints to make the either or happen. Right. So to explain, just to show it again one more time, but I'll show it very quickly because we have done this before. We're going to now just play around with values. So let's say if I say x1 equals 0. If x1 is equal 0, I'm not making any units of product 1, which means in that case, it is supposed to be allowed because we said x1 should be less than or equal to 5 or x1 should be greater than or equal to 20. Can't have it in between. Okay. So I'm going to say, okay, let's see if this would work. So I go substitute into this formula where it is x1 minus 40 plus the dummy. So I'll just write the dummy 1 plus 40 times our dummy, less than or equal to 5, less than or equal to 20. So if I substitute dummy as 0, I'm first going to check if that would work, but dummy must be the same. If that doesn't work, the dummy changes to a 1. If that still doesn't work, then the value is not allowed. So we check. 0 minus 0 is 0, less than or equal to 5. That's true. 0 plus 0, 0, less than or equal to 20. That's true. Both are true, so the value is allowed. That's what we wanted. That's good. Now I'm trying to say, but what if x1 was equals to 10? So now we substitute 10 into x1. 10. Start of dummy as 0 and we test it. Okay. So 10 minus 0 is 10. I don't even have to continue. I already see a false. So it's not going to work for the dummy as 0. It does not work. Okay. You can then go show also minus 10 plus 0 is, that's true. But because there's a false, it's false. Now I go and say, but what if we change the dummy to a 1? Because it can jump between 0 and 1. But if the 1 value is 1, the 1 must be 1. Remember, when you solve, you only get one single answer. So for example, here in Solver, you'll see you get one answer for the dummy, not a 0 and a 1. It can only be one answer. Right, so if the dummy changes to a 1, it changes to a 1 for both constraints. Now we got check. 10 minus 40. It's going to be minus 30. That's then true. Minus 10 plus 40 is a 30. That's false, so it's still false. So no matter what I do with the dummy, even if the dummy is equals to 1, this value does not work. That's perfect. It should not. Because we don't want in between. So, yay. Then the last one we will test is, but what if x1 was equals to, I don't know, 30, something higher than that? You can always go test what was the max value of x1 and make sure it can use that value. You can try it. Choose a 40. So that you can actually use the max value. So we try the 40. So x1 is now 40. Let me just click somewhere else. And 40. Then we're going to have our dummy as 0 first. You could have made it 1 immediately, but for purposes of testing. Right. This is just testing, hey? This is just testing if it works. Because you should be setting up the constraint to work for all the conditions. So you're testing that it actually does do what it's supposed to do, that you didn't have to multiply somewhere else or use a minus instead. All right, so let's see. So the top one would be 40 minus nothing. So I can immediately see false. So dummy 1 equals 0 will not work. Now we could change it. We say, okay, what if the dummy is equals to 1? 1, 1. So that then becomes 40 minus 40, which becomes a 0 there. So that becomes true. For the other one, it becomes minus 40 plus 40, 0 less than or equals to 20. That's true. So it does allow 40, which is perfect. We want it to allow 40. Right. So I hope that makes sense. And Marizon, yeah, if we want to test you, we should give you values. Otherwise, there will be just too many possibilities. So if you want to test, we'll ask you, okay, show how this would work or prove that this would work, this value would work. Yeah. If we don't, then anything goes. But then, yeah, it's going to take forever to mark. Unless if we give you very small upper and lower values that you can't have many choices. But yeah, I highly doubt that. I think we'd rather give you values. I hope this helped a little bit, just as a recap before obviously the test. I hope this helped. I'm just going to erase everything. I don't want my Excel sheet to stay like that because this is mine. But I hope that helped a bit. Just want to look at some location problem. Just have a look there. Let's see. All right. Oh, really, I could have just said no. Okay. And show there. Let me close that. You guys did not see anything. You don't know anything. Okay. Going back to location. Fixed charge. Please do all exercises. Okay. Going back to location. Let me first tell you inset covering. Attempt that QB publishing. It's very difficult, but it's a very nice one. You can attempt the others as well. It's quite nice examples, but specifically do that QB publishing. Because I'll do some parts of it maybe tomorrow if we get some time. Otherwise, you have the solution. All right. Then for knapsack, the one in the slides, definitely there's some solutions there. And there's even more here that you can do. But do the one in the solution, and then we can work with that. Just one thing, though. For this bottom problem, it's a bit out of scope because you'll see the number of coins. So it's not a binary problem anymore. So it's more like if you want to try it, go for it, but it's not something we would expect in the test. So this problem here. All right, so just giving you a heads up so that you don't sit there like, oh, how am I going to do this? Like, yeah, you can go try it and do some research. Quite nice, but it's not necessary. The rest are what you can do. Okay, then conditional constraints. I told you that Excel sheet, please. That's very important. Go watch some of my videos. Go look for other videos. The more you do, the better for logical constraints, or we actually call them conditional constraints. Certain conditions need to be met. If, then, either, or. If this, then not this. If both, etc. Then location. Let me go to location. This one. Okay, so the warehouses one, I actually wanted to just have some kind of sense there how to work with that one. Okay. You guys still with me? Just want to double check, otherwise I'll be talking to my screen. Cool, thank you. All right. So the warehouse problem. So in this case, they're talking about considering putting warehouses in different cities. So it's almost like the lockbox, except it's not a lockbox, it's now a warehouse that they're going to either put in or not. They're not talking about number of warehouses. They're just saying considering opening warehouses in the 4 cities. So you're either going to open a warehouse in Sydney or not. Either going to open a warehouse in Perth or not. Yeah, so you're going to have Y variables for that specific warehouse instead of location. Then they say each warehouse can ship 100 units per week. Oh, but now I can't use just binary. I mean, if I have a limitation or a certain requirement regarding the amount of units, then I can't just have binary variables. I mean, how am I going to take 1 + 1 + 1 and say it's going to be 100 units? Yeah, only have 4 cities, can't go more than 4. And if you take the matrix size and you say 4 × 3 is 12 of those numbers in the table, if I add those all up, it can't go 100 if it's binary. So I'll use binary for the warehouse to say whether I'm going to open a warehouse in that city or not. But I'm also going to need a variable to say, okay, how do we check the amount of units? Right. Now in this table, you'll see there's a from and a to. So from and to, and the from and to is not the same. So it's not from region 1 to region 1. So you're most likely going to use Xij. Right? Obviously, you're going to have to think about it a bit. But guys, I can see different values all over. And the from and the to is not the same. Whether it's symmetric or not, they're going to have different values that needs to go in an objective function. So I usually say focus on what you want to do with the objective, and then it will help you more to determine what to do with your decision variables. So if you check there, it's desired to meet these demands at minimum costs. Now I check, where do I see costs? Okay, I do see fixed costs for the warehouses. So I need Y1, Y2, Y3, Y4, because those are fixed costs. Then, so just to move my mouse, fixed costs. All right, so I need Y1, Y2, whether a warehouse will be open or not, and then they pay that cost or not. Okay, so that must be an objective. Okay, so I know I need Ys and binary Ys. Okay, now I say, but what else do I see in terms of cost? The from and to has certain costs in the table. So I need to include each of that cost to be able to minimize the costs to ship everything that I want to ship. So then I already see, okay, 20 from Sydney to region 1 is, and if I look from region 1 to, let's say 2, so region 1 to Perth is 48, but let me just think, 1 to 2 is 40. So 2, 1 is 48 and 1, 2 is 40, not the same value. So in my objective function, I'm going to need Xij to distinguish the differences. All right, so asymmetric, now you kind of have an asymmetrical table where you have different values. Some might be the same, but you've got different values. So you're going to have to then stick to the Xij method. That's one way of looking at it. All right. Then let's see. The cost of sending, meeting, okay. Then at the bottom, we've got two of those conditional constraints. But let's just look at the basic one. So if I go and set this up, maybe just do this. So if I go and set this up, I'm going to have some X variables, ij. So I'll say from I, which is our Sydney, Perth, Brisbane, and Melbourne, to J, I'll just say region here so we know. Okay. In my objective function, I want to minimize costs. So I'll go and say, oh, okay, min Z, for example, 20 X11, because that's from the I1 and J1, plus 40 X12, blah, 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 blah. That whole table must be here to minimize that. But then I have to go and say, okay, I have additional costs in terms of fixed costs. So those are my Y variables. So I'm going to need some Y variables. So Y is specifically, they keep a warehouse open for cities. So the which is my I. So I keep that the same. So I don't have to rewrite Sydney, Perth, Brisbane. It's still the same thing. But it's whether there's going to be a warehouse or not. So I'm just going to say bin. So whether there's going to be a warehouse or not. Just to show you, if you get lost a bit, it is in here to show you, okay, the Xij is this is this is going to be the whole objective plus all of these Ys, just to show that. Okay. Oh, where's this now? Right. So now I go and say, okay, I minimize costs. So am I going to subtract? No, because everything is cost. So I'm not going to subtract those Ys. I'm actually going to add them. All right, so with the Ys, I'm going to go and say plus. For Y1, it's going to be 400, Y1 plus blah, 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 blah. For Y2, blah, 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 blah. All right, so that's the objective. Now for the constraints, you'll see there, region 1 of the country requires 80 units per week. Am I going to work with Y or Xij when I talk about a requirement for the amount of units? You can tell me. We want to limit the amount or demand a certain amount of units per week. Are we going to work with Xij or Y? You have a 50-50 shot. So region 1 of the country requires 80 units per week. Am I going to use Y variables to do that or Xij variables to do that? If I take the Y variables saying I want to set it to, so just to make it clear, 80 units per week. Will I be able to get 80? Let's say Y3, Y4. We'll still decide on the sign. Will I be able to? Y variables are binary, whether they're in the city or not. There could be a way, but they do not tell us the answers, if I can put it like that. They do not tell us how many are going to be shipped specifically from region 1, for region 1, sorry. So for region 1, I've got these costs, but we don't know how many units are going to be shipped. So I can't put a value in front here and say definitely that amount. Yeah, so we can't use the Y's. I was hoping you would answer yourself. They're very good. So we're going to use the Xij. So for the binary, we can't use because if it's all ones, I mean, you're not actually comparing the units then to the actual units. So you have to use Xij, yes. Okay. If they say region 1 of the country requires 80 units, if I say they require 80 units, which sign am I going to use for the constraint? Require 80 units. They require 80 units or 70, whatever the region requires. Yes, greater than or equals to, because they need that. They need it. It's a must. They can have more, it's fine, but it's a must for 80. Okay, so greater than, because you can't limit it to just 80. They're not saying they have to get 80 on the dot. They just require 80. If they get more, oh, so be it. Right, logically speaking, they should get more than 80. It's not going to be very logical to say this one must be 80, this one must be 70, this one must be 40, because then I have answers. Okay, so now let's look. Which variables will I refer to if I say region 1? You can tell me. I is from Sydney, Perth, Brisbane, Melbourne. J is region 2, region 1, 2, 3. So which variables am I referring to if I want to limit the amount of units for region 1? Perfect. So for region 1, it is from Sydney to region 1, which is 1, 1. Perth to region 1, 2, 1. Brisbane to region 1, 3, 1. Melbourne to region 1, 4, 1. Don't lie, it's not a guess. But XI1, perfect, right? So XI1, where you have the sum of all of them. I starts at 1 and ends at, there are 4 of them. Right. Right. So that I can then limit to demand greater than or equal to 80. Region 2, you then go check which ones are for region 2, give a constraint. Region 3, which ones are for region 3, give a constraint. Okay. So then we have another thing. Each warehouse can ship 100 units per week. So again, are we using Y or Xij? Y or Xij if I'm saying 100 units. Xij, perfect. So I'm zooming in here a bit. So Xij, you're just going to go and say each warehouse can ship. Can I ship more than 100? Let me just zoom out again. Each warehouse can ship that amount per week. Can they ship more than that? If they're telling you they can ship 100, then we're assuming no. Why would they tell us they can ship 100 if they can ship more? Right, so you cannot ship more than 100 per week. So we have a limitation there. Now let's see if you can connect the dots. Is the warehouse going to be in the region or in the city? Is the warehouse going to be in the region or in the city? Good, in the city. So if we want to limit how many units are going to be traveling from a certain city, so meaning a certain warehouse, now be careful. A lot of people would have gone immediately and said, warehouse 1 is Y1. And then they would have said less than or equals to 100. You can't do that. Yes, warehouse 1 is Y1, but that is whether or not the warehouse is going to be in city 1 or not. So this can only be a 0 or a 1. Never the amount of units. So you can't do that. So you have to use all the X variables specifically for city 1, because that's where your warehouse 1 will be. Okay. Which variables are the variables for city 1? Let's see. Can you guys get that? Which variables are specifically for city 1 or Sydney? Correct variables, but no coefficients, no. In terms of x1, x2, but you had to have xij though. Remember, the variables are xij in this case because they all have different coefficients. Yes, Caitlin has it. But just to make it clear, no coefficients here because those coefficients are costs, not units. So you'll see Australian dollars, and they say the costs are in this table. So you won't be including costs if you're checking how many units. Xij is already the amount of units without any coefficients. Right, so just to make that clear. And then city 1 is then, if you look at row 1, it's going to be 1, 1, 1, 2, and 1, 3. Right. So that's where these come from, to tell you they can't ship for each city. It's going to be 100. City 1, city 2, city 3, city 4. So that's where all of these constraints come in. First constraints, we format an equals 1, equals 1. Where does the equals 1 come from? Oh, are you thinking in terms of making sure there's a warehouse? Let's see if they specify something quickly. Normally, I think you're thinking about the task assignment to say, okay, there must be a warehouse in each. Let's just make sure that that's what they say. If they don't say anything, then we won't necessarily specify that there needs to be a warehouse in each city. Okay, so no, they are considering opening warehouses in those. So it's not a must that there must be a warehouse. So if they said something like they have to put a warehouse there in each, then you'll put in constraints to say, okay, we want to make it equals to 1, but you won't be using your xij. Remember, xij is referring specifically the units from Sydney to region 1, the units from Sydney to region 2, etc., etc., etc. So if you're using xij, you're saying the amount of units. Now you're saying the amount of units must be equals to 1. That does not make sense. If you use your y's, which was binary, then you can say, okay, y1 must be equals to 1. Then you're forcing it to have a 1 for y1, meaning that warehouse must be in that city, right? That's if they forced us to say there must be a warehouse, right? Okay, I'm going to show the Excel just now. Just want to quickly talk about this part. So I'm sure you were probably getting to that piece technically. If Sydney warehouse is opened, then the Perth warehouse must be open. So before I show Excel, if the Sydney warehouse is open, I'm referring to city 1. If the Perth warehouse, I'm referring to city 2. Am I going to use xij or y to set up this constraint? Am I going to use xij or y to set up this constraint? Think carefully. Xij is the number of units. Y is binary, whether there will be a warehouse opened or not. Perfect. So we're saying if Sydney warehouse is opened. So I'll be using the Y variable. Yes, I'll be using the Y variable to specify whether it's going to be a 0 or 1. So Y1 and Y2. If they're talking about the amount of units, then I'll use Xij because that was my amount of units for the from city to region. Right, so whenever you need to restrict then units or integers, you'll be using the integer variable. So in our case, Xij. If you'll be restricting in terms of whether or not, or yes or no, or not necessarily if and then. I mean, it could have been if this, then we need 100 units. I'm just saying, like, if it's in terms of whether or not it will be open or not, it's like a yes or no, then I'm using my binary variables. All right. I'm wondering, let me think about that. No. At most 2 warehouses, so unfortunately, Xij is still the amount of units for each. So if you were to say the amount of units, it does not help me to use Xij at all. Because Xij is just the amount of units from each city to each region, but it never tells me whether there's a warehouse or not. So sadly, again the Y. Because the warehouse is very specific to the Y's. Just like the lockbox is to the Y's, or whatever variable you made the binary ones. Right, so that's where these two come from. Right, but you saw now, earlier I told you, we want equals rather for either or. Please highlight this for yourself. I want this. I don't want greater than. I want equals. Right. So either or, I want to literally have, just to show you, Y2, that's now for, I gave an extra example there, Melbourne, and Y4 is Perth. So if we set up a constraint for that, I want to make sure it's either this one or that one, not both and not neither. All right. So if we go and we say a 1 and a 0, I want that to be true. A 0 and a 1, I want that to be true. But not none and not both. So either or we take literally as either or. So I need a sign that would work for everything that is true and exclude everything that is false. Right. Did I now swap them around? Oh no, we had to do a plus in the middle, sadly. We couldn't put a sign in the middle just like that. So we had a plus there. That's going to give you 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And 1 plus 1 is 2. So what I can do to include only the trues and exclude the false would be make it equals to 1. Then this is included, that is not included, that is not included. And that's what I want. So it was literally Y2 plus Y4 equals 1 to have it as either or, because that's what we want, just to make it clear. Okay, but then for the other two constraints, they are here at most 2 warehouses. You're adding all the warehouses and binary values together. So if they are going to be opened in that city, it's going to be a 1. If it's not opened, 0. Opened, 1. Not opened, 0. And then that total will be added up to give you what they specify, at most 2. Right, just to make that very clear. Yeah, with Xij, it would be extremely impossible, kind of. Well, you can probably get a way to make it work, but I mean, you're working with the number of units from I to J. So going from the amount of units, then you first need to figure out how many units is the actual answer before you can go set up and say, okay, I've got this amount that I'm going to divide by the X to make sure that it's in terms of a 1 or a 0. So why not just go directly in terms of y's, which we do have? Okay, it's not impossible. It's just you don't have the answers, so you can't really use xij there. So whenever you get some kind of constraint, you have to think in terms of what can I use in terms of my variables to make those constraints happen. Okay. Binary variables, you use true and false, but if you use a dummy, well, you're still doing the true and false, Vian, where you went and said if the dummy is 0 is a true, blah, blah. And with these integers, you technically can still do, let me think of a way to help. Because remember, Vian, when we had yesterday in our slides, we had where we said, what was that? If something like x1 less than should not happen, then x12, x13, something, but these were actually our binary values. And then we had that whole upper of 3 and 3 times that. So it's not necessarily, unfortunately, there are some patterns, but it's not specific to int or binary. All right. So you go look at some patterns, but obviously it's not necessarily. So that Excel sheet that I provided gives you kind of a general way of seeing what is possible and what not, and what to do when, but it's not always. All right. But yes, mostly when you use the upper and lower limits, you use dummies, definitely. A pattern would also be if you see either or, if, then, and let me think. And maybe more, let's say more than 2 variables for binary, then you'll probably go, you don't need to for binary. No, you do. Then you need to multiply something like a 3 or a 2, depending on how many variables are there. So you can still use that formula, yes. But if it's only 2 variables, then the either or if then is as simple as saying, I do this method where I just play around and get the values. Right. But when it's more, then I have to start thinking, maybe I might need a dummy, especially if I need 2 constraints to do that either or. All right, if I only need 1 constraint, just this method. If I need 2 constraints to make it happen, then I start thinking about a dummy. Okay. I hope going through this a little bit will also help you. I really hope it will help. But that's all I got for today. Any questions? Nope. I think the set covering went a bit too quick, if I'm being honest. But obviously you need to practice. Like sometimes it just makes sense when I show, but then doing it yourself does not. So even this one, if you haven't done it yet, please go and do it from scratch to see if it makes sense. All right. That I don't know. Then Armandre, we finish with combinatorial. Combinatorial will be your last topic for week 2. But yes, it's in the study guide. Thank you, Jock. Yeah, we've done everything except combinatorial. The IEP is quite large for combinatorial, so we'll probably start with it tomorrow already, if we have time. But yeah, the solving is it's literally just combinatorial. It's just taking steps. Yeah, that's pretty much it. Now we're doing that on Thursday. Tomorrow we'll start with it, but only if we have time. Thursday will be the topic. Right. Yes, it is in the test, just like I think it specifies in the study guide. I cannot promise. I mean, if it's not asked, it's not asked, but we follow the study guide to set up. So if we ask something, it will be one of those topics. But one of them will definitely be knapsack or combinatorial IP and algorithm. So one of the algorithms will definitely be there, if not both, but one of them will definitely be there. IPs definitely. IPs will be there. The linking part, yeah, sure, I can show that. Because this one is quite different. Not different, but it's a little bit different, sure. Let me just show you there. So Y1, I'm just going to focus on Y1 and then you will probably understand the idea there. So Y1 is specifically for Sydney or City 1 warehouse, whether it's going to be open or not. So you need to make sure you have a link for that specific Y1 cost. Then we say, okay, but how do we create that constraint? So it still follows the whole X something less than or equals to a max value for that X and the Y for that X. Okay, it doesn't have to be the same number, guys. You already saw now we had a Y2 for X1 and X2. Right? It doesn't have to be the same number. Your Ys are a different variable, so you have to make sure you use the correct variable. Right. So here we go and say, okay, it's Y1 specifically for City 1. But now in terms of our X variables, we have different X variables for City 1. We actually have in that table, it's Sydney to region 1, region 2, and region 3. So you get 3 different variables from City 1, which is Sydney. So it's actually X11, X12, and X13. Those are the amount of units that would have been added up for Sydney. Right. So to make this X's link to the actual warehouse, you have to use those variables and connect it to this warehouse, because a warehouse will be opened. If it will be open in Sydney, it will handle those X variables. So we're going to say, okay, so that's going to be X11 plus X12 plus X13. Less than or equals to some max value Y1, because that's the warehouse we're linking to those variables, because it's specifically for City 1. Okay, now we're going to say, okay, but what's that max value? Now here you don't have to do any calculation. Some of you would have gone here and said, oh, okay, let me do this. No, that's greater than. There's no restriction there. They're saying make more. They demand more, but there's no restriction. If you can make more, what's your limit? I mean, infinite? So more than is not what you would use. So when you do your max value, you're only looking at less than constraints. Oh, this is quite useful. Hey, pattern. There's another pattern. Wink, wink. Use less than constraints if you want to get the M value. All right, so you've got these. So you could have used this, or you could have just read into it. I mean, without even looking at these, didn't they just say that each can only have 100 units? I mean, it's in the scenario without even looking at my constraints, where they say literally each warehouse can ship 100 units. So your M value is 100. They can't go more than 100. But if you were to use the constraints, I mean, which variables am I looking at? 1, 1, 1, 2, and 1, 3. That's the only less than or equal to constraint for 1, 1, 1, 2, and 1, 3. So then I can go and say, okay, if, let's say, I don't know, this one was a 0, and this one was a 1, that was a 0, the maximum amount would be 100. Okay, because they can only be, they could have been 100 in it even, but I'm just saying, like, if you substitute only the one So let me show you like this. If that was 0 plus x1, 2 plus 0 there, the max would be then 100, because 100 divided by 1 is still 100. So the m value is just purely 100. The y that matches is y1, and it's all three of these. Okay, so you still follow the same principle, but your m value. No upper or lower, no. The linking constraints are as simple as saying which x less than or equals to max value and which y, even if it's more than one x, right? Because there could be more than one x that refers to the same y. Cool. Anything else? Going once, give a shop if there's something. Going twice. All good. Armandra, I'll go check your teams in a few minutes, but otherwise I'm not gonna show you anything else, review anything else. So tomorrow we'll go through set covering exercise, some of it, knapsack, some of it, then review. If we go over, then we go over. If we have time, we'll go to the next topic. On Thursday, it's then combinatorial IP and algorithm. And then exercises, and then we're done for the week. All right, but let's see how it goes tomorrow. But for today, I'm done. But you saw now there's a lot of practicing. Redo these on your own, because in a test, the scenario changes, everything changes. Same concept, but everything changes. So you need to struggle with this on your own before it's going to stick. Right, but from my side, nothing else. Good luck. See you guys tomorrow.